I would like to welcome our next presenter to the session. Milecia McGregor.
It's pronounced Milecia.
Thank you, Milecia. Yeah. Her talk is on using reproducible experiments to create better machine learning models. Milecia's senior software engineer. She's an international tech speaker and mad scientist that works with hardware and software. She tries to make anything with JavaScript first. And in her free time, she enjoys learning how to ride a unicycle and playing with her dog. So with that, welcome to PyData Global, and I'll turn the session over to you. Thanks, Milecia.
All right, sounds good. Let me perform the magical feat of sharing my screen. Hey everybody, my name is Milecia and I'm a developer advocate at iterative.ai, and I mostly work on our open source tool DVC, which helps you make reproducible experiments. But if you have any questions and you want to ask them just like to me directly, you can reach out on the Slack, or you can reach out to me personally on Twitter at Flipped Coding. Or if you want to get into like some technical details behind the open source stuff, you can reach out to the whole team on Twitter at dvc.org. But with that being said, today I want to talk to you about using reproducible experiments to make better models. So let's just jump right in. There's some common issues that come up whenever you're making machine learning models. Doesn't matter what the particular problem is. It doesn't matter what solution you go with. It's just some things that pop up. So one of those issues starts with our original search for the best combination of hyperparameters, whatever algorithm or algorithms we need to use in our data set. So it's basically like us having a map, and we put all of these little different points, and we're hoping that wherever they cross, we find our treasure, which is our really good model that we can get to production, right? So we're trying to find this combination of all of these different things. Like hyperparameters are so very different from algorithms, which are completely different from data sets. And we have to find what works the best. So something that happens is that you start trying all of these different things. Maybe you start with a neural network, and then you see that's not quite the right approach. So you shift radically to some linear regression model or whatever it is. But every time you make a change, you have to keep track of all of those changes. And what happens over time is that it's just really hard to follow everything, because you have these different experiments where you've been testing out models, and it gets to the point where you're like, well, this model looks really good. So it has this great accuracy that's way higher than anything we ever hoped for. The loss is really small, and it doesn't take that long to train. So you have this great model, and then somebody asks you, well, what did you do to get this model? And you're just kind of like, I think this is the one that I used this random forest classifier on, or maybe this is the one where I had the learning rate set to 0.5, or maybe I was using that data set that we got a month ago, but then, you know, the business requirements changed and we got this updated one a couple of weeks ago. So you have to keep up with all of those changes. And it's interesting the different tools that teams use for this. So some people use spreadsheets where they have links to their Git commits and links to their data set, which is some kind of zip file on Google Drive. Some people try to take all of their experiments and put them in individual zip files where they have the data, the code, and the hyperparameters or whatever other configs. But the thing is, over time, when you're doing all of these little changes, it's just hard to remember which one was the good one, which one did you learn something from. It gets really messy really fast. So how do we actually fix that problem, right? And the way that we do that is by making our experiments reproducible. And to make an experiment reproducible, you have to keep track of all of those little bitty changes you make when you're running experiments while you're trying to figure out what the best model is for your problem. So let's say you decide you want to update the hyperparameters. That's an experiment. And then let's say you want to update your data set. That's a separate experiment. So what we really need to do is have a way to bundle all of these changes for us and be able to go back to any previous experiment, because maybe you've been running experiments on your model for 2 weeks and you figure out, oh, I remember that one thing from last week that told me my accuracy was like 85%. And then you're stuck with this problem of like, how do I get back to that model? But when you have something tracking all of those changes for you, you don't have to worry about the reproducibility part because every experiment is tracked. So I'm going to set this up with just a little background on hyperparameter tuning, because if you've done any type of machine learning work, you've probably run into some hyperparameter tuning at some point. So usually, well, just in case you haven't, I do want to let you know what that is. And hyperparameters, first off, are the parameters that define your model. So these are the things like, if you have a neural net, it might be the number of layers in that net. Or if you have a random forest classifier, it might be the max depth for that algorithm. So these are the kind of parameters we're looking at. Things like your learning rate, maybe a momentum somewhere, maybe some kind of min split, but they're the parameters that define your model. So you can't get them from training, you can't get them from, well, really anywhere. It's a lot of guesswork, which is why you end up running a lot of different experiments to figure out what is the best set of hyperparameters for your model. And a couple of common methods that are used to do this are grid search and random search. So grid search is a very exhaustive search. And let's say, for example, you have 3 hyperparameters. You have a learning rate, a momentum, and I don't know, let's go with a max depth. So you have these 3 hyperparameter values, and you've assigned each of them 10 values each, because you think somewhere in this range of numbers is your optimum. So with a grid search, you will go through every possible combination of those hyperparameters. If there's an optimum to be found, grid search is definitely going to find it. But on the other side, we have random search. So even though grid search will eventually find that optimum, it takes a lot of time, a lot of resources, and a lot of experiments. But with random search, you still have those 3 same hyperparameters. They still have those same 10 values apiece, except instead of going through each possible combination, random search just kind of hops around and mixes things together in maybe a specific way if you're using something like a Bayesian or Gaussian thing, but most of the time it's just hopping around, checking different combinations of values. And what happens is usually random search finds a better optimum than grid search in a similar amount of time, just because random search tests a wider range of values for you. So how does this all actually fit into what I'm talking about with reproducibility and tracking experiments. It's where DVC comes in because it's a tool that does all of that for you. But DVC is something that is open source, so you can look at the code for yourself and see what's happening. It works on top of Git. I know a lot of the other tools out there, like maybe MLflow or TensorBoard, they're great. Like, don't get me wrong. If you have a use case for them, you should definitely use those. But something that DVC does differently is it works on top of Git. So it has a way to connect your code and your data. So you get the code versioning through Git and you get data versioning through DVC. And all of that is combined in this nice little package that is completely unopinionated. So you don't have to import anything into your code. There's no libraries for you to use. You don't have to call an API to track things. You just run this in your terminal and it handles all of the experiment management for you. So with DVC, you can have hundreds, thousands of experiments, and you don't have to worry about tracking anything. DVC just kind of works in the background as you're doing these different, like maybe you're training your model to see what the metrics are around it. DVC tracks all of that. So it gets every little code change you make. It keeps track of all of those different combinations of hyperparameter values, which if you've done hyperparam tuning without a tool, it gets very tedious trying to keep up with those little changes because it's like, well, my learning rate was 0.5 here. That didn't work out. So let's see what happens when it's 0.1. And then you have to get the data set and zip it up. You have to get the code and zip it. You have to get the hyperparams and zip it. And then somehow you're supposed to be able to look at the metrics for this later on. Yeah, it gets messy really fast. So that's why we use tools to make those things easy for us so that we can focus on the machine learning part. So with DVC, if you run an experiment, you'll just be using this little command at the top, the DVC exp run. And what it does, it takes your code, your data, and any configs like your hyperparams, bundles it together, and then you have your reproducible little packet that lets you go back to any experiment because it has a record of the exact environment that you ran this experiment in, which if you've ever had to deploy a model to a different environment, you know how much of a difference that can make when you don't have the exact same conditions. So DVC is just one of those tools that lets you pack all of this together without you having to really think about it. You set it up in your project, you connect it to your Git repo, you connect it to any like remote areas. Maybe you have your data on AWS, maybe you have it hosted in Azure, and you connect all of these things to DVC, kind of like you see in this picture, and it just tracks it for you. So what's happening after you run an experiment is exactly this. It takes your data, whatever the data set is for that experiment, it tracks that, it tracks your hyperparams, of course, and it tracks your code. So not only is it keeping track of all of this, it's also making it really easy to access the metrics for each experiment so that you can get a really quick view of what you might want to go back to, what direction you might want to take your experiments next. It just bundles everything up really neatly for you. So this is an example of us running an experiment with DVC. And as you can see, we have a couple of hyperparams here on the right with our train.nest and our min split. Those are just two hyperparams that we're tuning for this little example. And then we have our metrics that we're following. So we have this average precision and this rock AUC value. But this is what the table looks like with just one experiment. By the time we finish this, this table is going to be so big that it won't fit on the page. But let's go through a normal flow of hyperparameter tuning. So you decide that you want to tune your hyperparams to, get better performance out of your model, maybe get that last 5% of accuracy that you need, or whatever metric it is you're trying to get. So you get your hyperparameters and you have the values for each of them. So you want to set up a queue of experiments because, again, when you have to run through all of those changes, just sitting in front of a computer, waiting for an experiment to run, and then you literally increment a number by one or by some fraction, it gets to be a lot. So with something like DVC, we give it all of the values for all of the hyperparameters, and it sets up a queue of experiments for us. So before you even get to the stage where you run one, this is what the table looks like. And what this allows you to do is, let's say you're working on a team with other machine learning engineers, and you're all running these same kind of experiments. So before you run your queued up experiments, you might want to check with them and be like, hey, did y'all already try this set of hyperparameter values? Is this a direction that we should go in? And they can look and see this combination right here before you run anything and be like, well, we haven't used these values yet, so it'd probably be worthwhile to run those experiments. And what you would do when you're ready to run them is just use this command, this dvc exp run all, and that runs every experiment in your queue. No matter how many you have in that queue, it will execute all of them. So that's something to keep in mind if you're thinking about offloading some of this training to some kind of cloud environment. You don't have to sit there and just watch them run. You can come back and look at them later. And something else that DVC does, if you wanted to run these experiments in parallel, so that maybe, you speed up your time for tuning, or you have some kind of resource constraint, you can do that. So DVC gives you a lot of flexibility with running multiple experiments. But after you've run everything, then you probably want to look at the results, right? So we show those results in the table, and you can see now we have all of these different hyperparameter combinations, and we have all of these metrics associated with them. So each experiment, as you can see over here on the left, has an ID associated with it. These IDs are how we are able to throw in that reproducibility. If at any point you decide that one of these experiments looks like it's something you should dig into, you can just take the ID of that experiment, apply it to your workspace, and it will load in all of your code, hyperparams, and data to give you the exact results that you see in this table. So we're looking at this table after we've run all of these experiments, and you see we have a pretty wide range of average precisions, all the way from 46% up to 50%. So maybe you decide that you need another eye to look at things because maybe something just feels a little weird to you about this. So you decide you want to make up a plot to show everybody on your team, because that's what we do, right? We take experiments and we compare them. So you run that dvc plots diff command with whatever experiment IDs you want to compare, and you get these plots just like this. So here you can see, the precision versus the recall, TPR versus the FPR, and all of these metrics are actually coming straight from your training script. So it's not some magic that DVC is doing. It's just referencing the JSON files that you produce from your experiments. So that is all that's happening here. That's all that shows in the table as well. So you take these plots to your colleagues and y'all sit around and talk about them and decide, you know what, we need to run more experiments. So you set up a queue of experiments again, and this time maybe you decide, well, I don't have time to finish out the rest of this grid search. Let's just random search some things. So we get these definitely random values over here for our hyperparameters. Again, we queue them up just so that we can check with our associates to see, has anybody seen any values in this range of hyperparameters? If not, of course, we're just going to go ahead and execute them. So we'll run all of our experiments and then we'll look at the table again. And now you see these values are looking really, really similar. So maybe there's something about this 90 to 125 range for the NEST. Maybe there's something to this, I don't know, between 300 and 500 for the min split. But you're able to look at these metrics right here. You don't have to go into some other tool. This is just a table that's in your terminal. Like, that's it. It's just a CLI tool that you use, and it shows you all of this information without you having to sign up for anything. You don't have to log in anywhere. You don't have to make API calls to anything. It's just here. And you see your metrics really easily. You see your hyperparams associated with them really easily. And you decide you want to run more experiments because those values are all too close together. So we set up our queue again, and we have a different set of hyperparameter values here. And we're just going to go ahead and do our regular thing. We'll run them and we'll look at our table. And, you know, it looks like something did a little bit better. So maybe this is the direction we need to go with our experiments. But before we do that, we'll probably consult with everybody on the team one more time. So we'll take them this plot that has an experiment from one of our previous runs, and it has an experiment from today. So we look at these and we definitely see there's a decent difference between them. So you'll talk with your team, figure out which direction you want to go, and then just continue running these experiments. So by the time you're finished, you get some table that looks a lot like this. And imagine back in the beginning, before we used a tool like this, trying to keep track of all of this so neatly. So each of these experiments has data associated with it. It has code changes associated with them. It has all of these different hyperparameter combinations associated with them. And can you imagine having to keep track of all of this just with a spreadsheet and some zip files? That I've had to do that before, and it's not fun and it's not easy. And when you do want to go back, you have to hope nobody else has messed up a row on the spreadsheet. So having a table like this to look through and having a tool that lets you easily go back and forward through your experiments as you try to figure out which direction you actually want to go before this model hits production. And not only before it hits production, but what exactly do you deploy to prod? Now you know the exact things that you have to deploy to production to get the results that you expect. So hopefully this table took away some of that anxiety from trying to do all of these experiments and track them just by yourself, or even if you have a team that you work with. It's going to be really, really hard to keep track of all of those experiments between everybody and be able to share them, compare them. This makes it easy to do all of that. But I do want to just wrap up with a few key takeaways to leave some time for questions. But the first thing, adding reproducibility is so important because you don't want to get to that point where you do have this incredible model and you showed everybody on your team how well it performs. And then everybody's in agreement that, yes, this is the one that should definitely go to prod. And you have no idea what exactly to deploy to prod. So then you have to start digging through all of these changes, going through Git commits, zip files, and it gets messy really fast. And it takes a lot of time to just try to sort through everything. But when you have reproducibility from the beginning, it's just as simple as referencing an ID and you get all of your changes back. And of course, DVC helps you do this because it's keeping track of everything in the background. You don't have to worry about what your hyperparams are at the moment. All you have to do is run your experiments, and then you can go and look at the metrics and how well they performed. And the last thing I really, really want to emphasize, of course, I was talking about DVC today, and of course, I would love it if you checked out DVC, but I totally understand that there are a bunch of other tools out there that are targeted at MLOps. So kind of my challenge to you for today is just go check out some of those tools. Maybe, hopefully, DVC is the one that you really like, but if it's not, there's stuff like MLflow and TensorBoard and a bunch of other products. So just try them out because these tools are here to make your life easier. You don't have to implement this thing. You don't have to write the code for it. Just check out the tools, see what works best for your processes, and go with it. Because even though it might be a pain, you can always change later. But with that being said, want to wrap up and leave some time for questions. And again, you can ask me questions now. You can ask them on Slack. You can ask me on Twitter at Flipped Coding. Or if you really just want to dive into DVC and you want some help getting things set up or debugging, feel free to join our Discord channel. A lot of people come in there just to get help getting unstuck on their projects, and we have the time. So, are there any questions?
Milecia, it's Jennifer. I'm wondering if you have anything you'd like to see added to DVC that would be helpful in where do you see the expansion there?
I think honestly a lot of stuff that we have on the roadmap are things that I've been kind of asking for. It's like DVC is such a powerful tool that it'd be nice to have just commands that make it easier to get started with experiments, and that's on the roadmap. So instead of just like having to set up everything, you can just set up the part that does experiments. So I'm pretty excited about that coming out soon.
That's great. Well, that's something to follow for addition maybe next year on your wish list. Thanks for joining us and your discussion, and for being part of PyData Global 2021. And thanks everyone here for joining.